The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI Web Sessions are recorded at ACI Conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI Conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
So our next speaker is actually going to be Thano Drimalas from the University of Texas Austin, one of Kevin Follier's postdocs now. Is that correct? Yeah. Apparently Sean could not make it, so Thano will give this talk here.
Perfect. Thank you. Thanks, Tom. So this afternoon I'll be going over deterioration of concrete due from potassium acetate. A lot of this work in this presentation is from Sean Heyman's PhD work. He's actually finishing up right now at the University of New Brunswick. We've also done some of the work down at the University of Texas. And this project was pretty much sponsored from the Portland Cement Association and also from EPRI, which is the Electrical Power Research Institute. So I'm going to kind of start off here and kind of go into a little brief background on kind of why we went to all the laboratory types of tests later on in the presentation. Well, I think we've gone over a few different types of deicers and anti-icers so far today, but I just want to kind of go over that we are going to be mostly on potassium acetate during this presentation. So potassium acetate is a commonly used anti-icer and deicer on airfield pavements. It's used because it is very effective and it's very non-corrosive to aircrafts, and I know we're happy we don't have airplanes out there that are corroding. And this has actually been a big topic here within the past, let's say, decade here in the United States, because we are seeing a lot more deterioration on some airfield pavements that are that have potassium acetate applied to them. This is actually an airport runway here at a joint. And you can actually see severe cracking occurring here. This is with a severe, highly reactive aggregate that was placed at this airport. However, at the same airport, it was a large project, and they actually used 3 different quarries, so 3 different aggregates on this airfield pavement. And an interesting thing was, we had some aggregates that were moderately reactive, some were highly reactive, and some were actually pretty much non-reactive at all, or maybe minor ASR, you could see. What was really of interest to us was, with this, let's say on C here, with C is, it's non-reactive aggregate. However, we do see actual damage occurring on this section of pavement. And we sent out these cores from all these different sections of it and out to 5 different petrographers, and they found no signs of ASR occurring. And there was I don't have a picture of it here, but there is damage occurring in these specimens right at the upper 5 millimeters of the surface. You do see paste alteration occurring, and like I mentioned earlier, this was a non-reactive aggregate occurring here, or that's in it. That's in the concrete. And if you look at the section of runway, on the left-hand side here is that non-reactive aggregate with no potassium acetate that is sprayed on this section here. That's what they told us at the airport. However, on the right-hand side here is where they do spray the potassium acetate with that exact same non-reactive aggregate. So you can see the difference between the areas that are not sprayed with potassium acetate. So there's a zoomed-up picture there of that section. Just a couple items here. potassium acetate and ASR. I think we do know that if we do have reactive aggregates, potassium acetate can exacerbate the expansion that is occurring. So that's expected, like we saw in that picture, like slide 2 or 3 of that joint. Interesting, we're seeing potassium acetate, with this deterioration with airfield pavements that are containing non-reactive aggregates. So that's, kind of, puzzled us, so why we kind of went to more work into this area. And, we did see the substantial paste alteration from those cores from the airport. So we want to look more into this. So our research objectives and what I'll be going over the rest of this presentation is, what are the mechanisms behind this non-ASR related distress that has been observed, and what is the rate of deterioration in field conditions, and is there a way we could prevent this deterioration from occurring? Can we use fly ash or slag to slow this down or not have it occur? And will non-ASR distress occur under field conditions, for example, in concrete with non-reactive aggregate exposed to potassium acetate? So we looked at this we did laboratory testing. We also did some field testing, and I'll just jump right into the laboratory testing. So we did paste and mortars in which we immersed in potassium acetate solution, and we did that 4 different temperatures: negative 5C, 5C, 20C, and 38C. So pretty much from below freezing all the way up to about 100 Fahrenheit. And we used a commercially available potassium acetate solution. It's a 50% solution, around a 6 molar concentration. And we also made 1 molar and 4 molar reagent grade potassium acetate to see what would happen at lower concentrations. And again, we looked at straight cement mixes, slag, silica fume, and a wide range of fly ashes with different calcium oxide contents. So this is paste. So there are no aggregates in there. So if anything does expand, it would be no ASR is occurring in these specimens. Just highlight here for the next couple graphs that are coming up. We have a very low calcium oxide fly ash. So we have a class F and 2 class C fly ashes and a slag. And what I want to get out of these 4 graphs here is first is we are seeing expansion with just a paste with these bars that are in potassium acetate, and as we increase the temperature here, we are actually seeing deterioration. We're seeing more expansion. We're actually seeing the deterioration occur even quicker. So you can see the x-axis here. We're at 900 days. We're at 38 Celsius. Things fall apart by 56 days. This is just an image of a paste bar with 25% Class C fly ash at 20 degrees centigrade. And again, this is the type of damage that you see. This is after just a couple months. And so from this slide here, I just want to show you that again, we have paste here, and it's at 4 molar and 2 molar potassium acetate concentration. And you can just tell, from 1 molar, even a 4 molar, we hardly see any expansion occurring in these specimens. So even just from a 6 molar to 4 molar, the expansion is a lot less than what it was at the 6 molar concentration. We made a bar with a couple mixes with 30% silica fume. Of course, that's not going to happen in the field, but we just wanted to make sure is there something out there with enough silica fume out there to be able to control the expansion. This is a 30% bar in water. This is at negative 5. This is at 5 centigrade, and this is at 20 centigrade. As you can see, as you increase that temperature, things get worse, and that's what the bars actually look like. So something else is occurring in the specimens. So now I want to kind of switch over to mortar immersion in that 6 molar potassium acetate solution, and this was done with Ottawa sand, which we know is ASR non-reactive, and we looked at it at 5, 23, and 38 degrees centigrade, and looked at Class C and Class F fly ash. As you can tell, I'll quickly go through this slide, and I'll go more in depth in the next slide. But again, as we increase the temperature, we get a higher rate of expansion. We get the rate of expansion that's occurring earlier, and we get a higher ultimate expansion. And if we look here, we do see some expansion even with the control in Class F fly ashes. This group here is everything with 20% Class C fly ash, and if we look here, that's with 40% Class C fly ash with the different types of ashes that we looked at. So it's almost similar to sulfate attack, with the more Class C fly ash you put in there, the worse it gets. So we're interested to see what was going on there, why this Class C fly ash was actually making things worse. So that work was done at the University of Texas but however, this one here was done at UMB. They used a limestone sand, which was also non-reactive. They looked at -5, 5, and 20. I guess since they were in Canada, they wanted to go lower in temperature. But they only looked at Class C fly ash, but they found very similar results. Controls were down here, and again, the Class C fly ash exacerbated the expansion occurring. Next few slides, I'll be going over some quantification of what we think is occurring within these samples. I have a couple XRD slides and then some backscatter images. So this is a control paste. The bottom XRD graph will be the bars that were just placed in water, and the top one will be bars that were placed in the potassium acetate solution. And what we see with the ones that are stored in water, we have ettringite formation. Of course, we have our Portlandite. However, once we put everything in potassium acetate, you don't see the ettringite there anymore, and you actually start forming a arcanate, which is potassium sulfate, and a calcium aluminate phase. So we think these two are forming from the depletion of the ettringite. We do see a little bit of a Portlandite depletion as well. And similar thing whenever we looked at these Class C fly ash mixes. Again, ettringite will go away. You start forming these calcium aluminate phases and arcanite in your samples. So these two, this is with mortar now, the exact same thing that we saw with the paste. You're losing your ettringite and you're forming something else in the system. Or you're forming arcanite and calcium aluminate phase. This is just a backscatter image here. This is some monosulfate, and right next to it, we have monosulfate with high levels of potassium just right next to it. And then even right next to it in the same area, we're actually seeing a formation of this C4H19, or a calcium aluminate phase that is occurring in the system. So, we see this stuff. Is this what's actually causing the expansion occurring? We think it is, but we're not 100% sure yet. But this is what we think is the cause of what's going on. And we also have this potassium sulfate and the arcanate forming also in these samples. So what was interesting is, we saw the same with ettringite. So we're like, let's make some bars with a type 5 cement where we have, hardly, any ettringite formation. We did a calcium aluminate cement. We also did a rapid setting calcium sulfoaluminate cement, which is like an ettringite-based system. And right up here, so this is the CSA cement after 3 days in water, and very high ettringite peak. And after 4 days, then in potassium acetate solution, this is what the bar looked like. And again, we get that calcium aluminate phase, and we get arcanate phase in there. So it's kind of worrisome because you have these airfield pavements, and if there's ever a problem, and then you do a fix on the roadway or on the pavement, they'll probably use some sort of rapid set repair. And if they do, you could get even quicker deterioration on that fix they just did. So everything I went through so far was on laboratory paste and mortar. And so what we noticed was, ASR is not present in these samples. And expansion occurs, without aggregates, and expansion, also is occurring with no non-reactive aggregates. We are seeing this formation of potassium sulfate and calcium aluminate phase. So I kind of went over all the laboratory testing, and now I'll kind of go into the field testing that we have conducted. And that's an outdoor exposure site with concrete samples, both in Texas and also in New Brunswick. And then also a bridge evaluation of a bridge that has a anti-icing system built in. So the concrete that we did where we made 3 by 3 foot by 6 inch slabs, and we did expansion measurements and profiling to see the depth of the potassium and how far it got into the actual concrete. Like I mentioned a second ago, we also did a bridge evaluation. These 2 items down here are bulk diffusion tests and effective sample size. I'm not going to talk about that. Will all be in Sean Heyman's dissertation. So at the University of Texas, we cast 16 slabs. We looked at reactive aggregates and also non-reactive aggregates. And again, we looked at Class C and Class F fly ash. And we made half the slabs, and then the second half of the slabs. So we had one set that was just the control, the exact same slab, the same mix we actually sprayed with potassium acetate. And the exact same thing occurred in University of New Brunswick, but they had 36 slabs up there. Again, looking at reactive and non-reactive aggregates, and again, Class C, Class F, and slag mixtures. And they also looked at the low alkali cement to see if they had a low alkali cement, if they could actually exacerbate things with putting potassium acetate on the slabs. In Texas, really doesn't get cold that much, so we never, if we ever did wait for a nice storm or any cold weather, we would probably never even hit these things with potassium acetate. But so we decided to actually spray it once a month, October through March. However, at the University of New Brunswick, it was applied before and after each snow event to simulate anti-icing and deicing. However, in January 2012, they started to apply it more often, especially when the temperature dropped below 0 centigrade, to ensure potassium acetate was being applied constantly. These here are just a couple of slides showing the non-reactive slabs down in Texas. Again, this is our controls, which we're happy to see that they are non-reactive. But then after applying potassium acetate, we still aren't seeing any sort of expansion occurring in these specimens, and there's no visual damage occurring on the specimens at all. So with our highly reactive slabs down in Texas, we do have, our control. These are our fly ash mixes here, and after applying potassium acetate, we do see an exacerbation of expansion from that potassium acetate, which is something we expected to see, just because we know the potassium acetate will do that to the reaction. What is interesting is, in our mortars and our paste, we would always see the Class C fly ash doing worse than the controls. However, this is typically what we would see with, fly ashes. We would see this reduction in expansion, but with potassium acetate hasn't actually exacerbated the expansion worse than the control. Kind of just went over those conclusions. At UNB, these are reactive slabs. However, their non-reactive slabs have done nothing so far, and actually their reactive slabs have only had the control expand, and the effect of the deicers haven't made any effect so far on their specimens. And again, I talked to Sean. He said there's no visual damage at all on the specimens as well. This is just showing the application of potassium acetate on these reactive slabs that have low alkali levels. Since the other ones haven't gone yet, I wouldn't expect these to go yet. What Sean did was he took cores from these slabs, and he, after 3 years, and he profiled down to 15 millimeters, and then he analyzed them to see how far in the actual potassium has gotten into the slabs. And what's interesting, well, not really interesting, but so he only saw the potassium going in on the control slab made from the highly reactive sand. And it only, it went in 4 millimeters, but what he thinks is because the slab had already cracked due to ASR, the potassium has actually penetrated in just from this cracks that actually formed on the top layer of the slabs. So we also looked at a bridge deck that had this anti-icer system, and cores are taken from it, and also a bridge visual evaluation occurred on the bridge deck. And this is after 10 years of this system being in place, and we aren't seeing any sort of, potassium getting into the bridge deck. So in conclusion, ASR wasn't, present in the samples that we made in the laboratory. However, we were seeing the expansion occurring without any aggregates. So all we made were the pastes. We saw expansion occurring with non-reactive aggregates. There was a chemical reaction that we determined that was going on between etrinite and the potassium acetate, which was forming arcanate and a calcium aluminate phase. Concrete samples have not shown the same damage as shown on the airfield pavements, except for the reactive aggregates. And that could be, on the airfield pavements, it could just be applying a lot of this on the pavement before they're seeing any moisture, so they have that high concentration there. Whereas, these bridge deck systems that have this automatic sprinkler head system, they use temperature and humidity to activate it, so they know when moisture is about to hit. So that could be lowering the concentration of that potassium acetate. And like I showed earlier, even at 4 molar concentration, that damage was not as bad in expansion. And structures that use potassium acetate, anti-icers, and deicers should ensure that there are no ponding areas where potassium acetate could accumulate, which would give it less time to penetrate and cause deterioration. Any questions?
We got plenty of time, so any questions for Thano?
At the airport, we had the non-reactive aggregates, and you saw the mild tracking of the surface down to about 5 millimeters.
Yeah.
Did you do any profiling there?
On that pavement, was there? I think there was profiling done on that. And I don't think it. Do you remember, Kevin?
Yeah, we did some profiling. I think it was basically the over 5 millimeters plus or minus. Not a lot of penetration.
Thank you.
All right, thanks very much.